So welcome to our No Family Left Indoors. Today we're going to be talking about the life cycle of a star. So a star is born with Lisa Weiniger. She's a NASA Jet Propulsion Laboratories Star System Ambassador. That's a mouthful, but it's very cool. Our speaker tonight is Lisa. Lisa has joined us a few different times, but she is very knowledgeable about space, very knowledgeable about the stars. Yes, bring your questions forth because she's good. She knows her stuff. And as I said, she is a Jet Propulsion Laboratory Solar System Ambassador for NASA. So welcome, Lisa.
All right. Well, thank you so much for hosting me again. I really enjoy working with everybody from Cedar Creek Institute. And we've had some interesting chats in the past about all things to do with what I love, which is space and stars and planets and what goes on out there once we get away from our own planet's surface. So this evening, we're going to talk about stars. And one of the things that I didn't realize for quite a long time is that stars are actually kind of born. They go through a very specific life cycle, like most things that are in the universe. And so at some point in time, they end and they go on to become stars and other recycled things. So that's what we're going to be talking about tonight. And we'll have a chance to look at some videos and some illustrations and figure out what exactly happens when these stars are born and then later on get recycled back into new kinds of stars. So the first thing to think about is a star is like a gigantic engine. So it's constantly full of fuel and it's burning fuel and it's doing things with that fuel. So we look at, we all know twinkle, twinkle, little star, and we look up in the night sky and we see all these lights, and all those lights are stars. Occasionally we'll see some reflected planets that are we're able to see because of the light from stars far away. They're all different sizes. There are many different colors. It's hard to see that when you're just looking with your eyes, but they do come in lots of different colors. And the question is, why do they twinkle? Well, first of all, they don't twinkle at all. The light from a star is fairly constant unless there's a planet passing in front of it in an orbit. The reason that we think that they twinkle is that their light is getting bounced around and bent by the layers of our own atmosphere. So if we were on a planet or if we were on a moon that didn't have much of an atmosphere, they would be a lot steadier and stronger. But I kind of like the twinkling aspect of it. It kind of reminds me a little bit of all kinds of Christmas lights up in the sky. So then the question is, like if we look at stars, we look at this star right here, which looks kind of red and angry. How do we know just by looking at stars what kind of stars they are, what they're actually like? Because we haven't had the opportunity to go out and visit stars. We can't even get that close to our own star, the sun, because it's way too hot. But how do we know just by looking what different stars are like? Because they're all very different from one another. Well, one thing we can do is we can use different instruments and we can look at the color of the star. And the color of the star will tell us basically what kind of temperature the star has. And there's a really big wide range of how hot or how really hot a star can be. Stars are never cold because then they wouldn't be burning fuel. But some of them are a lot hotter or cooler than other stars. And we can tell that by their temperature. We can tell by looking at a star, generally speaking, the size of the star. And remember, the light that you see has traveled a really long way across the solar or the galaxy or the universe. And so the light that you may see coming into your eyes right now may have been given off by a star thousands and thousands of years ago, but it was so far away that it took a really long time for it to get to the point where we could actually see it. Sometimes we see lights from stars that don't even exist anymore. But we can look at how big it is by just examining it with a telescope. Now, in terms of like mass is how heavy something is for its size. So we can look and say, was this, something that's really small, but really, really dense, so very heavy? Or is it something that's really large, but it's not as dense, it's very gassy? Kind of like if we look at the planets in our solar system. So we know that the planets that are closest to our sun are small and hard and rocky. And we know that the planets that are farther away are big, but they're nowhere near as dense because they're mainly formed with different kinds of gases. And stars can be the same way. Some of the ones that are big and puffy are less dense, and some of the ones that are small are very, very dense. So we can tell that by looking at the kind of star. So one thing that's kind of a rule of thumb for stars is if it's really, really big, it's really, really hot. And the bigger and hotter it is, the faster it's going to burn its fuel. And you may say, okay, so what's the fuel in a star? And the answer is, for the most part, it's the lightest element that we have. It's hydrogen. So stars are kind of like big hydrogen engines. And so we're getting these reactions where hydrogen atoms are sticking together. That's called fusion. And we're going to talk about what happens when hydrogen fuses. So first of all, though, let's look at the hot versus the cold. This is kind of like the opposite of what you might expect. Because I think if something's really red, it's really hot. And if something's white or blue, it's really cold, like ice versus like a log in the fireplace. But stars are the opposite. So a blue-white star is going to be really hot. And if we look at how hot it is, it's saying here that the surface temperature, so the outer temperature, not even the inside of the star, but the outer temperature of the star could be 60,000 degrees Kelvin, which is over 100,000 degrees Fahrenheit. So incredibly hot. And if we look at the least hot kind of star, which is the red star, it's just a mere 3,700 degrees Kelvin. And that would be about a little over 6,000 degrees Fahrenheit. So you're like, oh, well, that's not much. But I mean, think about the surface of the Earth. For the most part, we stay in a kind of a temperature range between about, 0 to 100 degrees. And this is going to be, thousands of times hotter than that. So one thing we can say is they're really hot. Just some are incredibly hotter than others. And that's why the star can give off all that light and it can give off all that heat energy, because it's a great big ball of gas that's just constantly burning like a big furnace. Okay, so this is kind of where we're going to start when we talk about stars. I mean, think about it. If people's life cycles, you might go off in one direction, and let's say you decide to become an astronaut or an astronomer or whatever. You might go off in another direction and decide to become an artist. Okay, you're going to go through a different life cycle, and things are going to be different for you. And stars, interestingly, have kind of two main paths that they take in their life cycle. So almost all the stars all start in something called the Stellar Nebula. And when I think of nebula, I think of like Guardians of the Galaxy, because there's somebody named Nebula in that. But it's kind of like these big clouds, and we're going to look at some pictures of these big clouds. And after that, there's two directions, two kinds of paths in life that the stars can take. So if it forms into a pretty small average size star like our sun, it's going to take long. It's not going to burn up all that fast. It's going to have a pretty long lifespan because it isn't gigantic and burning all its fuel just as fast as it can. But at some point in time, that average star is going to start to, use up all its fuel. And when it's in the process of doing that, it's going to create something called a red giant. And I'll show you some pictures of that. And after the red giant burns up fuel and it ejects a lot of material, it'll form something called a planetary nebula, which eventually turns into a white dwarf, which actually sounds like something from a TV show. But so we're going to talk a little bit about what that's like. But remember, this is a pretty long process. So eventually our sun will go through that, but it's going to take a long time. But what if a star life cycle goes in the other direction? It goes into the direction of those big, massive stars. Well, they're really, really huge. And because they're really huge, they're really hot. And they burn up their fuel really fast. And so when things get really hot and burn really fast, you can see some super dramatic changes. So a massive star will burn for less time than an average star, but it'll turn into a red supergiant. And that supergiant will consume as much of its fuel as it possibly can. And then very dramatically, we can get a supernova. And I have kind of like an illustration of what it looks like when the red giant goes into the supernova phase. And then depending on what's left after that supernova, if there's less material hanging around, you can get something called a neutron star. But if there was a ton of energy and there was a lot of material that went into this whole supernova process, then you can get a black hole, which is this giant dead part of space that's just got massive amounts of gravity. And, we've got all these speculations about what goes on in a black hole. Is gravity bent in a black hole? And can a black hole eat a solar system? But one thing we just learned in the past few days is that Einstein was correct, and you can actually see light through a black hole, which we never had a picture of before. So I think our research on black holes is probably moving on a little bit more quickly than what we might have expected. Okay, so let's look at these cycles in a little bit more detail. And then remember, Ellen, if you have any questions for these, just interrupt me and I'll just answer them to the best of my ability. Okay, so I want to show you a video that my group has, or NASA has produced, and it basically talks and shows like briefly, like what exactly is a star and how does it work? So sit back and have a look at this e-clip. If I can get it to play, there we go.
Did you know that when you look up in the dark night sky, you are in a way looking back in time? It's really true. Much of the light you see coming from the stars has been traveling across space for thousands of years by the time it reaches us here on Earth. Some of those stars that you can see tonight in the night sky may have burned out thousands of years ago. If you have ever wondered where stars come from, how they change, and what happens to them when their life comes to an end, hang with me for a few minutes as this episode of NASA Launchpad takes a closer look at the life cycle of stars. And bonus, we're going to talk a little bit about how each of us is actually made from dead stars. Yeah, really. Most things in the universe have a life cycle. Thankfully, for some things, like these guys, the life cycle is incredibly short. But for other things like stars, the life cycle can be billions of years long. The life cycles for stars begin in giant stellar nurseries called nebula. If you look at one of these star-forming nebula, you will see beautiful giant clouds of dust and gas. How a star forms is a little technical, so let's hear an explanation from an expert.
A star is basically a nuclear furnace. It's this collection of mostly hydrogen gas, and at the center is really, really hot and dense, where you can actually get nuclear fusion occurring, and that's how you get the heat and the light from the star. In space, you have this collection of sort of diffuse gas and dust particles. It's just sort of everywhere in space. Occasionally, it comes together through gravity. It's attracted to itself, basically. And so you get these giant molecular clouds, they're called, these big nebulae. As that stuff comes together through its own gravity, you eventually get these places where you have enough material where you can start to form a star, where it all comes together and the gravity pushes on it so hard that it heats up in the center, and that heating up is what will eventually lead to fusion and the birth of a star. Two of the most important properties of a star are its color and its brightness. And so if you take stars and you sort of sort them by color, you get anything from red to blue, where the red stars will be the cooler stars and the blue stars will be the hotter stars. So that's really a measure of temperature. And then you can also sort them by their brightness. And so you have the very bright stars, which are usually the more massive stars, and the dimmer stars, which are usually less massive. And just by these two parameters, you can actually tell a lot from a star. You can tell how massive it is, you can tell how big it is, its radius, you can tell how old it is, you can know what stage of evolution it's in, and you can learn about the environment of the star, that the star was born in.
As you know, our sun is a star. It is actually a fairly modest-sized star. It is believed that our sun is about halfway through its 10 billion year life cycle. Yes, that makes our sun about 5 billion years old. But don't worry, we're all good for at least another 5 billion more years. So, how will our sun's life cycle play out?
So our sun is a low-mass star, and it's actually going to go through a really long evolution. It's going to be in the phase that it's currently in, where it's just fusing hydrogen into helium, for about 10 billion years. And then once it runs out of fuel in its center, it's going to evolve into a red giant star, a red meaning that it's going to be cooler, and it's going to be so large that its outer radius is actually going to reach the Earth's orbit. It's going to be a huge star. And then eventually it'll blow off its outer layers and become a white dwarf star, and that will be its final phase.
So at the end of a massive star's life, we have what's called a core collapse supernova. So the core region collapses in on itself, and the outer region infalls and then rebounds, and you get left with a neutron star or a black hole.
You may have noticed that no matter the size of the star, at the end of its life cycle, most of its material is expelled back into clouds of dust and gas in the galaxy. The life cycle of a star can begin again.
Throughout a star's life, it's throwing off material, and this material has been enriched by nuclear fusion reactions. So originally, really only hydrogen and a little bit of helium was produced in the Big Bang. And all of the elements that we get after that have been produced in either a star's life or in its explosion, if it's massive enough to explode. And that material gets mixed in with the other gases and dust in the interstellar medium and produces the next generation of stars. So every generation of stars that you produce is more and more enriched with material from the life and death of stars.
So what does all of this mean for us? And what is our connection to the cosmos?
All of that fusion that's going on in the centers of stars is creating heavier and heavier elements, and that's how you get basically everything you see around you, from the carbon to the iron, the oxygen, everything. You can't get any of those elements without having a star forming it in the first place. And so everything that your body is made up, everything that you see around you, all came from the center of a star.
Pretty amazing, isn't it? When you look at that periodic table hanging in your science class, it represents all of the natural and man-made elements. Most of those natural elements were formed and fused inside of long dead stars. Yeah, that's right. Almost every element in your body came from the inside of a star that died billions of years ago. We may look and act differently from each other, but we are all made up of the same stuff. Want to find out more? You can learn more about stars and their life cycles from these NASA websites. That's it for now. See you next time on NASA
Okay,
Launchpad.
so I'm just going to pause there for a minute. And if you want to learn more about stars from NASA, we have lots and lots of resources. But a couple of things to just come back from the movie. Number one is all of those elements that make up everything in our universe come from stars. And stars being born and stars dying and being recycled. Originally, we had just very simple elements. And over the billions of years, it's evolved into more and more and more complex elements. The second thing is, when I talk to students about our sun being halfway through its life cycle, they're kind of worried about, well, my goodness, what's going to happen when our sun uses up all of its fuel? You know, I just want you to think about the fact that it's 5 billion years away. And in human history, we went from the Wright brothers flying the very first basic airplane to putting people in orbit around the planet in 60 years, 60. So if we can move our technology along at that same rate of speed, we'll be able to travel to other planets and other stars long before 5 billion years goes by. And so we'll be able to find other planets that people can go and visit and perhaps live on long before there's any sign of our sun expiring. Okay, so let's go back and look at a couple of those things. I love this idea of a stellar nursery. Okay, so there's some place that we can look at and we can say, look at these formations of clouds and dots and lights. It's going to be where that stuff is that is going to come together with that force of gravity hard enough to make a reaction that's going to start a star forming. So just like people go through nurseries, so do stars. There has to be a place for them to gather together. So not that long ago, we found a gigantic star nursery right in the Milky Way galaxy, which is where our solar system is located. And if you look at the Milky Way galaxy, you can see that it has this spiral, right? These long spirally arms, and we're out on one of those arms in our solar system. But this area that's in the picture to the right, that little red dot area, is also on an arm. And it's an area where we can see stars forming and, you know, being able to spin off, perhaps to have their own solar system, or in some cases there are solar systems that have more than one star. Like if 2 stars, for instance, you had 2 suns in the sky, that would be a binary system, and they can actually kind of be in orbit to each other while they have planets in orbit to them. So imagine how unusual it would be if we had 2 suns and one could go up and one could go down. I don't know how that would affect us, but I think we'd be a little bit different than we are now. So stars start from clouds, and clouds are gas and dust, but it's not the kind of dust you see like at my house with, you know, the dogs running in and out and all this kind of stuff. It's a different kind of dust. Let me go back a little bit. It's little grains of carbon or silicon, very, very, very tiny, that kind of provide some mass to get pulled together. And so those grains they come together and they collapse into something called a protostar. That's like the beginning of a star, like the very, very kernel of a star. So that dust accumulates, and the force of gravity, which acts on anything that has mass, pulls it toward a center. And so that's called contraction. And when all those bits and pieces start to come together and move, it causes the temperature to rise and the pressure to rise. And if there's one thing we know, when there's temperature and there's pressure, we're going to see some kind of physical change that's going to go on here. Something's going to get different. So what happens next is called nuclear fusion. I think we all know, like if we're looking at nuclear power plants or whatever, they're doing nuclear fission, which is where you take atoms and you split them apart. And when you split them apart, you get energy. This is a different process. This is where we take atoms and they get squished together. And it's so hot, 15 million degrees Celsius in the center of the star, we basically are able to take atoms and fuse them into new kinds of elements. And when that happens, if we take 4 hydrogens and we fuse them together, we get 4 heliums and we get some electrons and some neutrinos, but what we get is a ton of energy. So if we could figure out how to do fusion here on the planet effectively, we could definitely do it with a tiny little bit of material. So the energy comes from the fact that the mass of 4 hydrogens is greater than the mass of 1 helium. So, or 4, so you put them together, you have a greater mass going into it than you have coming out. And a lot of people would say, well, wait a minute, you can't turn matter into energy. But I think that Albert Einstein would disagree with you, because he was the one that said that you could, if you had the right circumstances, you could convert matter into energy. And that's what happens with nuclear fusion. And there's a ton of this energy that's being created constantly in the cores of these new stars. Well, the question is, what's a ton? How much energy is there? And the answer is, we had just talked about it. So we take these hydrogens and they fuse together to create a helium, and it releases quite a bit of energy. And these may or may not mean a whole lot to you, but if we look at it, each little collision creates a tiny little bit of energy, but the sun creates that tiny bit of energy 10 to the 38th power every second. And it has, so many hydrogen atoms to burn. It can just keep doing that almost infinitely, or basically for 10 billion years. So there's so much energy that's just created by this process that it helps form the star. Okay, so if we're looking at how this works, everything in the universe is kind of a push-pull. One thing has to balance another thing. So we have got gravity pulling everything toward the center, but we've got energy coming out, and those two things determine how big or small the star is. How much gravity there is that's pulling it together, and how much energy there is that's trying to cause it to expand. And so when we look at like the average size star versus the supermassive star, it's really a question of how much fuel do you have and how quickly are you using it up. Okay, new stars. Now, this is not a gentle little process. The new star being created is a very explosive process. It's like almost, you'd say it's kind of violent. It'd be like, big, huge earthquake or something. So in this case, this is a binary star. If you look at the picture at the bottom, the 2 lights are 2 stars that are being created as a pair. And so in 1995, you see part of this expulsion outward, and then 98, and by 2000, it's just got this giant blast of energy that's coming away from these 2 stars as they're being created. All right, so in the video, we looked at this little diagram, and this is called an HR diagram. And basically there's some people, and one is a very famous woman, and they looked at stars and they said, how do we categorize stars? How can we figure out like which ones are more common and what are their characteristics? So just to look at this, what we have this thing that's called the main sequence. So this is where your average stars kind of live, and they range from very hot to less hot. If we look at our sun, it's kind of smack dab in the middle. So this would be like kind of your average stars that you would see a lot of. Down at the bottom for white dwarfs, they are very hot, but they're very dim. They don't have a ton of light. And up at the top, we have supergiants. So you can tell by the fact that they're really red that they're not as hot, but they're very, very bright. So if we look at classifying all the stars that could possibly be found in the night sky, they're all going to fall somewhere in this diagram, and over time they're probably going to change from one kind of star to another. So they're constantly, just like we change and we get taller and all kinds of things happen to us, stars continue to change over a whole lot longer period of time. So just to kind of go back, if we look at the life cycle of stars, it kind of goes off into two directions. The sun-like stars, which are the average size stars that have longer lives, they're not as huge. You know, they kind of go through a very predictable pattern. And then we've got these massive stars, and they have so much energy that you just know something big is going to happen with them. And it's going to affect what their life cycle and what the end of their life cycle is like. So if we look at the massive size, you know, when we start to get toward the end of the life of these massive stars, they go to red giants. And I just wanted to point out to you here, if we look at this red giant, which is located in this system, the size of the star itself, if you look at the diagram, it's much, much bigger than our entire orbit for our planet. So these stars are really, really big at the end. As a matter of fact, the one that's measured here is just slightly larger than the orbit of Jupiter in our solar system. Not Jupiter itself, its orbit. So imagine a star that occupied all the space in our solar system that Jupiter's orbit takes up. It would take out all the planets in between and our sun. So these are really, really large. And so what happens is they burn out all the hydrogen in their core, and that core collapses. And then all the energy gets pushed out to the outer layers, and they get really big and really huge and very loose. And the core continues to collapse. And so we know that when it gets pulled in, there's more temperature and then there's more pressure. And then we see it start to fuse pieces or matter into other kinds of elements. So we get this core collapsing again, and everything in it starts to fuse into the new kinds of elements, the things that we would see on planets, for instance. And it just keeps creating heavier and heavier elements by fusing together more and more and more of its materials. So this is how it works. So remember, hydrogen is going to be the lightest, and that hydrogen burns, and the helium burns, and the carbon gets burnt, and all these things keep burning to, you know, create different kinds of materials. It fuses together oxygen, it fuses together neon, magnesium, and silicon. But when we get to iron, it can't be fused any further. It's the most stable element. So instead of releasing energy at that point in time, it uses energy. And what is the result of that is we get a supernova. Like the super eerie kind of music, right? But the supernova is not the end of the line, because we know that, you know, elements are never destroyed or lost. They just either move away or they turn into a different form. So then what's going to happen after that supernova? So I wanted to show you some pictures here. This is a supernova that was imaged from, supernova 1987. And you can look at what's going on out in the night sky using different kinds of instruments. So this box right here is and it's basically looking at it from a telescope. And so the stuff that you see around here is the material that got ejected from the star even before it went supernova. And in B, we're looking at it using a different kind of imaging using radio waves. And you can kind of see this hot part still here, okay? With this, we're looking at it using X-rays. So remember, there's a lot of different ways you can see things, you can image things. And I just want you to look, this and this are about 6 months apart. And you can see what's going on right here is these are starting to cool down. These red spots are the cooler part. So over time, this is going to continue. And we see this shock wave heading away from the supernova itself. So now what's going to happen is the question. Here's another image of a supernova. So if we were to see what it looked like with our eyes, it would just look like a big bright blast, because our eyes can only see in certain parts of the visible spectrum. But if we look at it with an X-ray where we can see things even better and adjust it, it looks like a big giant fireball that is coming away from where this star had a supernova event, probably perhaps billions of years in the past, certainly millions of years. Okay, so after the supernova, remember we're in that massive star kind of category. After that supernova, it really depends on how big the core is, which direction this material tends to go. So if we have a core that's less than 5 times the size of the sun, essentially, we could get a neutron star, which is the protons and the electrons collapse and they form neutrons. It's very small. It's only about 10 kilometers across. But if the mass is bigger than about 5 times that of the sun, then you get a black hole. And the black hole is just like a super massive, dense part of space. And it can't be supported by anything. So black holes that would be actually a really good topic for a presentation sometime in the future, is to talk about black holes and where they are and what they do, because we're really learning a lot about them. So then that supernova stuff, it goes scooching out into space. And in the movie, they talked about the interstellar medium. We think about space as being this empty area where there's nothing. And that's not true at all. There's stuff in space. It's pretty spread far apart, but there's plenty of dust and gas and other things that are out there in space. So then the supernova blows up and it interacts with that stuff that's already in space. And so it gets enriched by what's there. And we get the compression of gas and dust. And guess what that does? That starts to form the nucleus of new stars. So it's kind of like a big, gigantic recycling project of the material of stars in space. Now, what if we talk about the kind of star like we have, like our sun? That's a solar type star. So, after all the helium that's in there gets burnt up, then we see the outer layer of the star start to change here. And these are 3 different examples of what happens. So we get Planetary Nebula. And that will eventually, inside of it, have a white dwarf, which again is a name that I absolutely love. White dwarfs are really cool. They're very small, but they're incredibly dense. And the description that we use is if it's the size of the Earth, but it would have the mass of our sun, and they call that a ton per teaspoon. So like imagine you put like a little sugar cube on a teaspoon, but that sugar cube weighed a ton. Okay, that's how dense a white dwarf is. So it's a pretty crazy thing. And the gravity pulls it inward, and then it's balanced by the electrons that are inside that white dwarf. So again, to keep it together like a snowball, you always have to have a force that pushes out and a force that pushes in, and then they have to be balanced for that star to hold together. Okay, so what that does is it brings us back to our example that we had again. So we looked at how all stars start with stellar nebula. Some go into the direction of being average or solar size stars like our sun. Some go into the direction of being massive, and they have a different life experience. But at the end, we know they all end up going back in as gas and dust and mixing up with the interstellar medium to start that whole process of stars again. So that's kind of the engine that drives the universe, is all of that process. And then the last part is, as stars are, go through their life process and start to use up all their fuel, they also create the elements that make everything else up that's in the universe, including you and me. Okay, so now the tricky part is, how do we know so much about stars when we've only ever even, been able to see them not that clearly? I mean, our own star, we've seen a lot more of, but how do we see these stars that are, outside of our own galaxy and other parts of the observable universe? And the answer is, like every other thing, it's technology. Because originally the technology that the ancients used was they just looked at the stars and they would map them, and they got lots and lots of information about how things work, but they couldn't really understand them in depth because there wasn't enough to go on. So, and I said thanks to Galileo. Galileo Galilei was one of the people who was involved in using the very first polished glass lenses to be able to look up into the sky. But a lot of other people worked on telescopes before and during Galileo's time. But now we use really, really complicated technology to be able to see really far beyond where we could with Galileo's telescope. So I've got a couple of examples here. The pictures that are on the left are ground-based observatories. So there's lots of them that you can go to all over the world The biggest ones are usually in the most isolated areas. They're on mountaintops. There's a bunch of them in Hawaii and South America, and they're as far up into the atmosphere as we can get and still be on the planet. And they use very large telescopes and combinations of telescopes to be able to see far beyond what you and I could do with our telescope that we have in the backyard. But even so, even with the biggest telescope ever, you're still having to look at that twinkle twinkle effect, which is everything we see is kind of bent and twisted by our atmosphere, which obviously we need to be able to live, but it doesn't let us get a really good picture of what's going on with the stars. So another example that you can see is the airplane there, and that is the plane that I flew some missions on, and it is owned by NASA, and it's called SOFIA, and it's a flying observatory. So this is a big 747 airplane, and it takes off into the night sky. And when it gets up to about 50,000 feet, which is where the atmosphere gets really, really thin, but there's still enough of it to hold up an airplane, then it opens up that big door in the back, and a giant telescope comes out of the side, and the telescope is about 12 feet wide. It's really, really large. And so for certain kinds of images, it's a great way to see it. And so if you fly on SOFIA as an astronomer, you know, the plane will go in a certain direction because you're looking at a certain star or a certain object you want to see in the night sky, and you get all your images, and then it turns in another direction. And right now, SOFIA is in New Zealand, and it's looking at stars that can really only be seen from the southern hemisphere. So that's another way to do it. And then the last kind of category of ways that we see stars are telescopes that are based in space. And the picture that I have there is of the Hubble Telescope, which is pretty famous. It's our first really, really big high-tech space telescope, although we've had other ones as well. And Hubble has been amazing. It went out to do its mission service, and it's just kept going and going and going. And recently Hubble shut down, and they were pretty worried that it was done, but they managed somehow to switch it back on again. And so Hubble is still out there, but it still can't capture everything everything that astronomers would like to see. And also one of these days it's going to shut down, and it's just never going to start back up again. So what we've got now coming online is the James Webb Telescope. And I want you to keep that in mind, because that is going to be the next big telescope that's going to make discoveries about the stars that none of us could even have ever imagined. It's set to launch in November of this year, and it's going to launch from French Guiana, which is down by the equator. And a lot of people ask me, well, why do we have to launch it from the equator? And the answer is it's the part of the Earth that's closest to space. So it's the easiest place to launch from, because you don't have to travel through as much as much distance to be able to get out to space. But let me show you a quick video about the James Webb Telescope.
The places where stars and planets are born are among the galaxy's most beautiful locales. These cosmic landscapes change as new generations of stars light up and disperse their birth cloud. But the youngest stars seen here are already perhaps 1 million years old. Hardly toddlers.
Stars and planets form in the dark, inside vast cold clouds of gas and dust, such as these pillars imaged by the Hubble Space Telescope.
The dust is so thick we can't see the infant stars inside, at least not with visible light.
With infrared light, Hubble can see through all but the thickest dust. Yet it's in those dense knots that the youngest stars are forming.
To peer inside them, astronomers need the James Webb Space Telescope.
With a mirror larger than Hubble's and performance optimized for the infrared, Webb will give astronomers their closest look yet at stellar birth.
We're flying through a computer model that represents astronomers' best ideas about the star formation process.
Reddish colors indicate thicker dust. The temperature, less than 400 degrees below 0 Fahrenheit.
Or less than 240 degrees below 0 Celsius.
That pinwheel ahead is a protostar, perhaps 10,000 years old. protostars arise when a dense knot of dust, less than a light year across, collapses. But the details of the process are not well known.
Elsewhere in the cloud, another protostar is preparing to build planets. As the cloud that created the protostar collapsed, it flattened into a disk. The disk we see here is 600 times the size of Earth's orbit around the Sun.
If placed in our solar system, it would extend far beyond the planets.
In this computer model, the disk continues to accumulate gas and dust from its surroundings for thousands of years. Eventually, the disk fragments, producing dense, bright structures. These may become sites where giant planets form.
Later, during another phase of construction, smaller Earth-sized planets may take shape.
At least, that's what scientists think happens. It will take the Webb telescope's keen infrared eye to see what's really going on in the cold heart of stellar nurseries.
So one thing to note from that is that the part of the electromagnetic spectrum that Webb is going to use is infrared. So it'll get to see things that are really, really hard to detect, but also the thought that it not only would see stars forming, but also the solar systems that are forming around them. And it takes a really long time for a solar system to form, and also for a star. But you have to remember there are billions of these things happening all at the same time. So they'll be in all different levels of development as we're able to look at them with instruments like the Webb. So if we understand how stars and solar systems form, and how stars and solar systems fall apart at the end of a star's life, then we can have a better understanding too of what's going on with our own solar system and what will happen with it in the future. Okay, so I always get a lot of questions, a lot of number questions, which are really hard to remember all the answers to. So I have people ask me questions like, how many stars are in the universe? So, you know, if we're saying 100 billion per galaxy, then we could say maybe a billion trillion stars that we can actually see in the observable universe. And then the question is, are there parts of the universe we're not even able to observe yet? In our own galaxy, the Milky Way, 100 to 400 billion. So we're a pretty star dense kind of galaxy. The closest star to us, Proxima Centauri, about 4.3 light years. And a light year is how far light could travel in a year. When you think about how fast light travels, that's a really long distance. It's about 25 trillion miles away. It's likely that that would be the system that we would travel to first when we leave ours, but we're going to need to learn how to move a little quicker. Because at 4.3 light years, you know, there'd be a lot of generations of folks that would have to travel before they'd actually get there at today's rate of speed. You know, our sun is about 4.6, 4.7 billion years old. Our planet is about 4.5. So you can see that relatively quickly after our star formed, our planet started forming as well. And how long does it take for a star to actually form? At least 10 million years. So when we look at them with the Webb telescope, you know, we're going to see all kinds of different stars in all different parts of their life, but we're not going to be able to sit around and watch one form from day one till 10 million years, because that would be way too long of a time cycle for any human being to be able to understand. So I would just like to thank you for joining me to talk about one of my favorite topics. I absolutely love stars and all things planetary, and I'm so happy that Pierce Cedar Creek Institute asked me to come out and talk to you again. If you have more information that you would want to get, like via email, you can email me at mynasa.gov, and I will be happy to answer those questions. Or Ellen, if we have any questions that I am capable of answering live and in person, I'll be happy to do that.
We do have a question. The one question we do have is, when you talked about all the fusing of all the elements, someone asks, well, when the hydrogen gets used up, everything will eventually be iron because it can't be fused? So when you were talking about everything fusing down, will it eventually all become iron?
Well, no. The answer to that, that, the hydrogen that formed, that's so abundant throughout the universe is really, the byproduct of the formation of the universe. So there's kind of, insofar as the universe is concerned, there's kind of an infinite supply of that. Only certain kinds of star development lead to the creation of the heavier elements. And for the most part, a lot of them go back once they get blown up, they kind of get recycled back into those other lighter elements. So a certain amount will become the heavier elements, but a large number of them won't. And there's also a huge amount of hydrogen that's still out there.
Makes sense.
I hope so. It's kind of weird when I answered it, but.
I do want to mention there aren't any other questions, but I do want to mention, I said I would say what the No Family Left Indoors code word was before I forget it. We are talking so much about stars today. The code word for your passport to fun is Milky Way. And so, so yes, we themed that well. One other question that came in is, how did all of the hydrogen form?
Oh, so that is the product of the Big Bang. Okay, so this is kind of a philosophical question, right? Well, there's a Big Bang. Like, what made the Big Bang? Like the expansion of some form of matter into a gigantic explosion that created our universe. But the question that comes with that is ours the only universe? Are there other universes that were created through other Big Bangs? Some people think that there's like a multiverse and we're all just like, bouncing around like marbles out there and whatever all of this is. And, but that's where the hydrogen that basically is the source of everything that is made in our universe came from, is the original Big Bang. I wasn't there though. I'm not quite that old.
None of us were there, we'll put it that way.
We'd have better answers, but right now, this is all like detective work. Yeah, we can take the evidence that we have and draw conclusions from what we know, and this is kind of the state of what we know right now. And maybe there'll be young people in our audience who are going to go out and find out way more amazing things and come up with some incredible discovery that will just turn all this on its side, and we will be happy for it.
Well, and just like you said, I think at the beginning, we're learning new things about black holes even, a few days ago, I believe you said. So
it's so amazing, but I was super happy for Einstein, because everything Einstein did, he did in his brain. He never tested anything. He just had all these great ideas and people are like, what? And since in his life, so many of the things that he theorized have been proven true. And now we know you can see light through a black hole. Crazy.
Wonderful. I hope you enjoyed our program. I hope you have enjoyed the No Family Left Indoors program. And thank you so much, Lisa, for joining us tonight and sharing your wealth of knowledge. It was great.
It was such a pleasure to be with you.
All right. Well, good night, everyone.